Hi, and welcome to 20 pumping lemma examples. We're going to be doing all 20 of these examples in this video. I included a timeline down in the description if you want to go to your question that you want to look at. I'm going to be doing a proof of all of these. So I'm going to start off with some easy ones, so ones that use the normal pumping lemma, just in a straightforward way. Then we'll get into some more intermediate examples. And then finally, we'll do 3 quite hard examples, and I'll show you the techniques to solve all of these. So let's get started. Okay, let's prove that this language is not regular. So how would you prove that this language is not regular? You always start every single proof of showing non-regularity by supposing that this thing is regular. So let's call this language L. So we're going to first suppose, so this is the first step, suppose L is regular. Then what we need to do is we know, we're assuming that L is regular, so that means that there is this pumping constant, we're going to call it P for this language L. So there exists a pumping constant P for this language L, which corresponds to a DFA of that particular size, but we're not thinking of the actual DFA here. Okay, so there exists this constant. So now we gotta pick a string that's in the language in length, total length, at least P. So the typical strategy here is that there are a lot of strings that you can pick. The strategy is whatever this number is, just substitute it in the exponent here. Well, there's only one type of exponent, it's just n. We're gonna have more complicated examples later. But here, we just substitute this p in for n here. So what we're gonna do is we're gonna choose a string w to be 0 to the p, 1 to the p. So I'm purely just substituting this p number in for the n. Remember that n is a variable right here because n ranges over all 0, over all integers at least 0. P is just some number, we do not know what it actually is. So I can't just pick the string 0, 1 as an example because I don't know that p is equal to 1. P could be 10 trillion. But this guarantees that the length of the string is at least p. In fact, it's at least 2p here, which is good. Okay, so what we need to do now is to look at every possible way of breaking this string up, because if we leave out any possible way of breaking it up, then it might be that that allows us to stay in the language forever. So if I show for every possible way of breaking this string up according to the rules, then and show that you can get out of the language at some point, then that means there's no possible way that this thing could have been a regular language because it would break the conditions of the pumping lemma. So what we need to do here is to look at all decompositions. So look at all decompositions. I'm going to shorten it to decomps of, spell of correctly, of w into x, y, z. I know other instructors use different variables. I'm just going to use x, y, z here. Such that, well, remember the 3 conditions. I'm just going to call them a, b, and c. Well, one of the conditions we're going to actually not do right now. The first 2 we're going to look at. So the first 2 pieces, x and y together, are at most p. And the length of y is at least 1. The third condition, that's going to allow us to get the contradiction that we care about. So, but we're going to leave that alone for now. So what are all the possible decompositions? Well, the x and y pieces are of length at most p. Well, remember that x and y are the beginning of the string. So look, x is at the beginning, y is next. So the beginning of the string, the first 2 pieces, are at most p characters. So the x and y are entirely within the zeros here. So that means that, well, it could be that the X and Y are a lot shorter than P characters, or it could be all P characters. We don't know for sure because we got to look at every possible decomposition. So all that we know is that X and Y contain only zeros and no ones whatsoever. So X is going to be some number of zeros. I don't know how many, but let's just say alpha zeros. So alpha is the number of zeros that X has, is the length of X. And Y could be a totally different number of zeros. I don't know for sure. Let's just call it beta for now. So what we know is that alpha is at least 0 because X itself could be the empty string. Well, we know that Y can't be the empty string because of the condition in the pumping lemma. So we know that that beta here is at least 1. That's all we know. And technically we do know that, although we're not going to use it, that alpha plus beta is at most P, because that's effectively saying this again. The length of x, y together is alpha plus beta, which is at most P, according to this. Okay, so what we need to do is we need to choose an I, and we got to look at the string x, y to the I, z. So y to the I is y repeated I times. So what we need to do is choose an I such that x, y to the I, z is not in L. Why do we want to do that? Well, the condition of the pumping lemma that I left out here says that no matter what value of I that you pick, you always stay in the language. But if I find one example where we actually leave the language, then that contradicts what the pumping lemma says, assuming that the language was regular. So that means that if we find an I such that this happens, then the language is not regular. So let's try to investigate what this is. So x, y to the I, z. Well, what I'm going to do is I'm just going to copy and paste the pieces down. I actually need to say what z is. Well, we know that z is the rest of the string. We're breaking up w into 3 parts. Well, the first 2 parts were these 2 pieces here. So z is the rest of the thing. So z is, well, it's got to have some number of zeros. It might have none, but it has some number of zeros. We started off with p zeros right here. We took away alpha in this piece. We took away beta in this piece. So we're going to have p, which is what we started with, minus alpha, because that's what the x part has, minus beta, because that's what the y part has. And neither of the 2 pieces touched any of the ones, so the z part has all of the ones. So it's gotten greedy. It has all of the ones. All right, so then what we need to do then down here is just copy and paste these down here. So that's what I'm going to do. So I'm going to copy and paste the x part, which is 0 to the alpha. We're going to have I copies of y. So the number of zeros for this piece is going to be I times beta, because I have beta for each one of them, and I have I of them. So I'm going to have I beta up here, and then just copy one of the z's. So I'm going to have 0 to the p minus alpha minus beta, 1 to the p. And what we notice is that we have a whole run of zeros right here. So we can collect all of the exponents together, which is what I'm going to do. So if we just add them all up, well, we see that we have a plus alpha here and a minus here. So those are going to cancel. So those 2 are going to cancel. So what I'm going to left with is 0 to the p plus I beta minus beta, because I have a plus I beta here and a minus beta here, and I still have all the ones over there. So the only way that this string could ever possibly be in the language is if these 2 exponents are the same, because that's what the definition of the language is. So what we need to figure out is choose an I, which is what we're trying to do anyway, such that the two exponents are different. So beta plus I beta minus beta is not equal to P. So then we see, okay, well, we got a P and a P here. So it's equivalent to saying, oops. So this is equivalent. I'm not trying to work both sides of the equation here. I'm showing an equivalent statement. It's the same thing as finding an I such that I beta minus beta is not 0, which is again equivalent to saying if I move the beta over, I beta is not equal to beta. And I'm going to divide by beta on both sides. And I'm allowed to do that because beta is at least 1. It's not 0. If it's something that's not 0, I can divide on both sides of the equation if I wanted to. So again, if and only if I is not equal to 1. So I just got to pick a value of I that's not 1. Well, it has to be at least 0, but it's not 1. So let's just pick I equal 2. So let's pick I equal to 2. That's clearly not 1. So therefore, we have found an I such that the resulting string is not in the language. And so therefore, that contradicts the for all statement in the pumping lemma statement. And so therefore, we're able to leave the language. And we looked at every possible decomposition of the string. And so therefore, L is not regular. Cool. So that effectively proves that this language is not regular. I've done it many times on the channel, but it's worth having a singular video about the topic. Okay, so let's prove that this language is not regular. So it's the set of all strings over 0, 1 star, such that the string has the same number of zeros and ones. So as an example, if I look at the string 0, 1, 0, 1, that clearly has the same number of zeros and ones in it. So that would be, let's call this language L. So this would be in L. But if I look at the string 0, 0, 0, 1, that has a different number of zeros and ones, and so that thing is not in L. Okay, so I want to show that this thing is not regular. So there are actually several ways of doing that, and one that's actually very straightforward. So I could go through the whole pumping lemma argument again, and I will do that, but there's one way that you can do it which is really quick, actually I'm going to call this language L prime for now. I may switch back to L, but I'm just going to leave it as prime. So let's look at L prime. Well, it's kind of like the 0 to the n, 1 to the n example. It's just slightly different in that we have any ordering of the zeros and ones. But in the 0 to the n, 1 to the n case, we had the zeros first and then the ones second after the zeros. So is there such a way that I can enforce the ordering with this without changing the regularity of whether this thing is regular or not? And it turns out we can. So what I'm going to do is I'm going to intersect this language, this same number one right here, with the set 0 star 1 star. So we know that this thing right here is a regex because it is a regex. So if this thing is regular, so if L prime is regular, then regular languages are closed under intersection, and so therefore this thing is regular. But what is this thing? Well, what is this set? Well, it's the set of all strings that have the same number of zeros and ones, and the zeros come first, and then the ones second. Well, that's just 0 to the n, 1 to the n. And we know already, because we've proven it before, that this purple thing is not regular. And so if L prime is regular, then the right-hand side is regular because we know this thing is regular. So the only possible way that this thing could not be regular is if the left thing is not regular. And so that proves that it is not regular. So from that, we have effectively shown that L prime is not regular. But suppose that we wanted to prove this straightforward, without any closure properties whatsoever. Well, the thing that we can do is use the proof of 0 to the n, 1 to the n not being regular verbatim, except changing L for L prime. Because why? In fact, I have the proof right here. So we've shown before that 0 to the n, 1 to the n is not regular. Well, let's see. So suppose I just change this to L prime, L prime. Well, here, this string is in the bottom language because it has the same number of zeros and ones. We don't enforce any ordering here, so as long as it has the same number, that's all we care about. So here, it's the same string. Therefore, all of the decompositions are exactly the same. So this is exactly the same. Well then, if we look at the resulting string, which is this one right here, the condition of being in the language is exactly the same. Because we're not changing where the zeros are over here, so we didn't have a structural problem with 0 to the n, 1 to the n. We have, we're just checking whether they're the same number or not, which is exactly what this condition is. So effectively, we can use the exact same proof as the 0 to the n, 1 to the n example, which is pretty dang cool. So what my advice is, try to use either closure properties or use the proof or adapt the proof of some other language to use for this language. And it turns out to be very, very powerful. Another closure property technique, which isn't very effective here, but we may see it later, is to use, say, like complement. If the language that we started out with is regular, then the complement language is also regular because regular languages are closed under complement. So if we can show that the complement is not regular, then that shows that the original thing is not regular. And sometimes that's a lot easier. So often we intersect things with regexes like this. It preserves the regularity of whatever this is. Well, actually it doesn't, but if this thing is regular, then the resulting thing is regular. So then the contrapositive is, if the resulting thing is not regular, then the original thing couldn't have been regular. So it preserves the regularity in that sense. So use these techniques, it's very, very useful. All right, so let's prove that this language, which I'm going to call L, is not regular, where W is any string in 0, 1 star, and W has more ones than zeros. So let's start the proof as we normally would. So we would suppose that L is regular. Then, of course, there exists a pumping constant P for L. So there exists I'm just going to shorthand it to call it the variable P for L, just for simplicity. So now what we need to do is we need to pick a string that's in the language and at least P characters long. So I got to pick a string, there are many that I could pick, where W has more ones than zeros and has P characters in it. So we could just try to model a proof like 0 to the n, 1 to the n, and let's choose the following string. So let's pick 0 to the P. Well, I gotta have more ones than zeros. So let's pick, let's say, P plus 1. Okay. So I could pick P plus 2 because that's more ones than zeros also. I can't pick 0 to the P, 1 to the P, no plus 1, because then it would not be in this language. It's got to start in the language, and then we pump out of the language. Okay, so then what do we do here? Well, we got to look at all decompositions, as we always do. So we got to look at all decompositions of W into those three pieces, X, Y, and Z, according to the rules that X, Y has length at most P, and Y is non-empty, so Y has at least one character. Well, since X and Y have at most P characters, and the first P of them are zeros, that means that X and Y only have zeros in them. So we know that X is going to be some number of zeros. Let's just call it 0 to the alpha. So alpha is the number of zeros that X has, or just the length of X. It's the same thing. And Y could be a totally different number of zeros. I have no idea what it is. I know that beta must be at least 1 because Y has to be non-empty. And Z is the rest of the string because there are only 3 parts. And just like the 0 to the n, 1 to the n proof, we're going to get something very, very similar. So note that Z has all of the 1s still, but this is the remaining set of zeros. Okay, so now what we need to do is we need to choose an I, or find a value of I, such that we leave the language. So let's pick a I. So let's look at X, Y to the I, Z, and see what values of I allow us to leave the language. So what is this thing? So X, Y to the I, Z. Well, we're just going to copy and paste the X bit. So that's 0 to the alpha. We're going to have I copies of the Y bit. So that's going to be I times beta upstairs. So I beta upstairs. And we have one instance of Z, so I'm just going to straight copy this down. 1 to the P plus 1. And like the other proofs, we have a section of zeros that we can just collapse all the exponents in. So the alphas are going to get killed off. And just like in the other proof, we're going to have P plus I beta minus beta 1 to the P plus 1. And of course, this is only going to be in the language if the number of 1s is bigger than the number of zeros. So this is in that language L if and only if P plus I beta minus beta, which is the number of zeros, is less than, strictly less than, P plus 1. And let's make sure that it's the 1s, not the zeros. Yep, more 1s than zeros. So this is true if and only if I beta minus beta is less than 1. So that means, so let's just factor beta out. So that's going to be beta times I minus 1 is less than 1. And so what do we know? So we know that beta is at least 1. So that guy is at least 1. So the only way that this could be strictly less than 1 is if we choose I to be 1. Because if we pick I to be 1, or I guess if we pick I to be 0, so 1 or 0 allows this inequality to be true. But we want the inequality to be wrong, so because we want to be out of the language. So let's pick I equal 2. So, but if we pick I equal to 2, then let's see, so that's 1 here times 1. So then let's try to investigate what the string actually is. So if we look at what the string actually is, so the inequality is false and we're done. But let's just actually see why. Well, if we pick I equal to 2, we have 1 beta right here. And so we would have P plus beta, there's 1 beta here, and then P plus 1. So we don't know what beta actually is, but we know that it's at least 1. So that means that the number of zeros is at least as many as the number of 1s. It might be more than the number of 1s, but it cannot be strictly less. So you actually can, for this very similar reason, pick any reasonable number plus whatever, and you will still find eventually an I that works. Because if we pick, let's say, 1,000 right here, P plus 1,000, Well, it could be that beta itself is equal to 1. But if I pick I to be 1001, then that will mean that this inequality will still be false in that particular scenario. So because we're pumping in the zeros, then that allows us to pump out of the language just by putting more zeros in and not changing the number of ones. By the way, you can actually, if you screwed up, you actually choose this other string, let's say 1 to the p plus 1, 0 to the p. So now you're pumping in the zeros, in the ones. Then if you put more ones in, then the number of ones is still going to be more than the number of zeros. So you'll never leave the language there. But since we have exactly one more 1 than 0 at the start, if we pump down, then we must take away at least one of the characters over here. And so we won't have strictly more ones than the zeros. This is what I call straddling the borderline of being not in the language. This is barely in the language, one character away from not being in the language. So that's just something that I would recommend doing. Here, if we have ourselves putting more characters in, we want to put the part that we want to put more of in at the start, because we can only take one away in the worst case scenario versus adding as many into the string as we wanted to. So this was a lot easier than this one, but we get the same conclusion, just done a different way. Cool. Okay, so I want to prove that this language, which is the set of all strings of the form 0 to the 2n, 1 to the n, where n is at least 0, is not regular. So here we'll use a standard pumping lemma proof technique. So let's suppose that L is regular. Then, as always, we need to pick a pumping constant P for, we know that there is a pumping constant P for this language. So there exists a P for this language. I'm just shorthanding saying pumping constant here. Okay, well now we need to pick a string that's in the language and has length at least P. Well, the common technique whenever you have n's and exponents and stuff is put the P where the n is. It doesn't always work, but it is generally a good idea. So let's choose the string w equal to 0 to the 2p, 1 to the p. And this is clearly in the language because I just substituted the number in, and has length at least p, well, length at least 3p, which is fine. So now what we need to do is to look at all decompositions, I'm just going to shorthand the word, of w into x, y, and z according to the two rules, which are that x and y together have at most p characters. So the first two bits have at most p characters, and the y bit is non-empty, so it has at least one character. Well, if x and y have at most p characters, and they're the beginning of the string, they must entirely consist of zeros. So, and I don't know how many zeros they have some number though. So let's just say x has alpha zeros in it. Y has, it could be a totally different number, let's call it beta. And we know beta is at least 1 because we know y is non-empty. And z is the rest of the string because there are only 3 parts. So we're going to have 0 to the 2p because that's what we started with, minus alpha because that's what the x part had, minus beta because that's what the y part had. And we have all of the 1s here because the first 2 pieces never touched the 1s. So we need to now choose a value I such that x, y to the I, z is not in the language because we want to escape the language, because that would contradict the statement in the pumping lemma, the fact that this was regular. So let's choose an I such that x, y to the I, z is not in the language. Well, what is x, y to the I, z? Well, that is, well, let's just copy and paste the pieces down. So we're going to have 0 to the alpha, 0 to the I beta, because we had y is 0 to the beta, and we have I copies of it. And then the z part I'm just going to paste down. So 0 to the 2p minus alpha minus beta, 1 to the p. And we have a consecutive run of zeros here, so let's just collapse all the exponents together. So that is the same thing as, well, the alphas are going to get killed off here because we have a plus alpha minus alpha. So we're going to have 2p, because that was not killed by anyone, plus I beta, because that's from the y bit, minus beta, because we have this minus beta here, and then 1 to the p here, because we never touched that. Okay, so we want to see when this thing is in the language, so we can pick an I for which it isn't in the language. So this is in the language if and only if. Let's see. Well, the language says that the number of zeros at the beginning is exactly twice the number of ones at the end. So that means that 2 times this number is equal to this number. So 2p plus I beta minus beta equals 2p. That's the condition to be in the language. Well, here we can just subtract from both sides. And this is the same. This is in L if and only if this is true. So we're going to have I beta minus beta equals 0. I'm going to add beta on both sides and divide by beta, because I'm allowed to do that because beta is not 0, it's at least 1. So that's if and only if I is equal to 1. And you can kind of see that here. Well, let's just pick an I that's not 1. So this is kind of like the 0 to the n, 1 to the n proof, but the condition to be in L is slightly different. So let's choose I equal to 2. And that'll be enough, because we're going to be adding some zeros in the beginning and not changing the number of ones, so the relationship of it being exactly twice as many is not going to be held anymore. Cool. So 0 to the 2n, 1 to the n is not a regular language. Okay, so let's prove that this language L, which is all the strings of the form 0 to the n, 1, 0 to the n, where n is any number at least 0, is not regular. So here it's kind of like the 2 halves of the string have to be exactly the same with the 1 separator in between. So let's suppose that L is regular. Then by the pumping lemma, there exists a pumping constant P for L. Let's use pink for this. So there exists, I'm just going to shorthand it to P for this language. So then now what we need to do is to pick a string that is of length at least P and in the language. And the trick usually is to substitute this P in for the exponent, and it's going to work in this case too. So let's choose W equal to 0 to the P, 1, 0 to the P. Note that this is in L because I just substituted the P in, and it's length 2P plus 1, which is definitely at least P, which is good. Okay, so then now we need to look at all decompositions of this string into those 3 parts. All right, notability crashed. I'll probably have to edit this out later. All right, my string went away, so let's choose it again. W equal 0 to the P, 1, 0 to the P. So now we need to look at all decompositions. I'm just going to shorthand the word of W into X, Y, Z, according to the 2 rules, which are that X, Y has length at most P, so the beginning bit has at most P characters, and Y is non-empty, so it has at least 1 character. Well, here, since the first P characters are zeros, and the first 2 pieces are of length at most P, So that means that x and y are entirely in this little region here. So we know that x is going to be some number of zeros. I have no idea how many, but it's some number. I'm going to call it alpha, whatever it is. Y is going to be some number of zeros. I don't know what it is, but I'm just going to call it beta. And we know that beta is at least 1 because y is not empty. And z is the rest of the string. Well, we have p, because that's what we started with, minus alpha minus beta zeros. We started off with p zeros and we took away these two. And we have the 1 separator still there, and all of the zeros at the very end still there. So then now what we need to do is to choose an I such that x, y to the I, z is not in the language. So let's choose an I such that x, y to the I, z is not in L, because the pumping lemma says that it's always in L for every I. But if we find one that is not in L, then that contradicts it and contradicts the fact that we suppose that this thing is regular. Okay, so let's investigate what this string is. X, y to the I, z. Let's just copy down the pieces. So we have 0 to the alpha, that's the x bit. We have 0 to the I beta, that's the y bit I times. And then the z bit 1 time. Oops, not z. 0 to the p minus alpha minus beta 1, 0 to the p. So here I have a consecutive run of zeros. And this one doesn't count because there's a 1 separator, but I can combine these ones because they're all zeros. I'll just put the exponents together. So the alphas are going to get killed off. So I'm going to have 0 to the p plus I beta minus beta 1, the separator, and then 0 to the p. Well, the only way that this thing could be in the language at all is if the two exponents are identical. So this is in L if and only if these two numbers are the same. So let's write that down. So this is in L if and only if p plus I beta minus beta equals p, because those are the two exponents. So this is if and only if I beta minus beta equals 0. And this is if and only if I is equal to 1. So if I choose any value other than 1, then we can find that this thing is not in the language. And I will just pick I equal to 2. So choose I equal to 2. And this is kind of like the 0 to the n, 1 to the n proof. It's structurally a little bit different because we got this separator and it's the same set of characters, but it's identical in the conclusion and how essentially the same in how we were able to show that this thing is not regular by finding a string that is not in the language. Cool. So we have shown that 0 to the n, 1, 0 to the n is not a regular language. Okay, so the next two proofs I want to do all in one fell swoop, and because they're very, very similar to each other. So that we can kind of do both of them in the same proof, but just slightly change it at the very end. So we have two languages here, which are zeros, ones, then zeros, of the form some number of zeros, some number of ones, and in the first case, the number of zeros at the end has to be the number of zeros in the beginning plus the number of ones at the end. And the second one is the product of the number of zeros and ones in the beginning. Okay, and I want to show that both of these are not regular. So what I'm going to do is I'm going to have a language L prime, or actually I'm going to change it to 3, which is going to be generalizing both of these, and then we'll hoist it back to the original 2, and we'll see how. So I'm going to have 0 to the n, 1 to the n, and then 0 to the f, some function of m and n. And then the first example is the function is just adding the 2, and the second language is just multiplying the 2. And then we'll see if and only if it's in L3, and then we'll see what the function is at the end. Okay, so this is m and n at least 0. Okay, so then let's suppose L3 were regular, then that means there exists a pumping constant P. I'm just going to shorthand it. There's a pumping constant P for L3. So then now we got to pick a string that is of length at least P and is in that language. So what I'm going to do is I'm going to just borrow this by substituting P in for the exponents. And it turns out that there are other parameters that will work here too for the first two languages, but it turns out that if you just substitute P, it's really easy. So let's choose W equal to 0 to the P, 1 to the P, and then 0 to the F, the function F on P and P. Just substituting M and N for P, or P for those two. So this is definitely of length at least P. Well, this function can't be worse than 0. So even if there were no zeros over here, I'll still have more than P characters to start with, which is great. This is in L3 too, L3 also, because I'm just substituting in the number P for M and N, and that's all we needed. Okay, so then now we need to look at all decompositions of this string W into those three pieces. So look at all decompositions of W into X, Y, and Z according to the two rules that X and Y are of length at most P, and Y is non-empty, meaning it has at least one character. So we have that X, because this string starts off with P zeros, that means that X and Y are both only zeros, but I don't know how many of them. So let's say X has alpha zeros, Y has some number beta of zeros. I have no idea what the number is other than is at least one. And Z is the whole rest of the string. Well, I'm going to have P minus alpha minus beta, 1 to the P, and then all of the zeros at the end, which is that F function P of P. Okay, so then now what we need to do is to choose a value I such that this is not in the language anymore. So choose an I such that technically we need to choose functions F1 and F2 also, such that let's see, such that X, Y, I, Z is not in okay, so I'm abusing notation a little bit. So is not in L1 or L2. So the functions are going to be different. Note that F1 corresponds to checking whether or not it's in L1 or not, and F2 is whether or not it's in L2. Okay, I'm abusing notation a bit because there's no F1 and F2 written here, but note that the F1 and F2 are corresponding to the function F that's written for what Z actually is. So let's actually compute what X, Y to the I, Z is. Well, that's going to be 0 to the alpha, because that's what the X thing is. Then 0 to the I beta. And then just the Z bit. So 0 to the P minus alpha minus beta. 1 to the P. And then I'm just going to write F here for now, because this is just a general case. Now let's check whether or not it's in L1 by substituting F1 in. So the F1 thing, well, F1 is just adding the two values. So here, this is going to be in L1 if and only if, let's see. So here what we have is that the number of zeros at the beginning plus the number of ones here equals, in this case, 2p. So what is the number of zeros here? Well, the alphas are going to get killed off. So we're going to have the number of zeros over here is going to be p plus I beta minus beta. So p plus I beta minus beta plus the number of ones here, which is just p, is equal to f1. Well, f1, remember, is just adding the two parameters. So that's going to be equal to 2p. So here, we'll notice that we got 2p over here. So this is, oops. So this is if and only if I beta minus beta equals 0. And then you can check for yourself that this is if and only if I equal to 1. And like other proofs we've done before on this channel, we can choose a different value of I. Let's choose it 2. We can pick 0 or 3 or whatever. All those will work. So then now let's do the other one. That this thing is in L2 if and only if multiplying the number of zeros times the number of ones equals P times P, because remember the second language had the two parameters multiply each other. So here, let's do, so we have P plus I beta minus beta times P is equal to P squared. So note that P is at least 1, so we can divide by P on both sides. So we're going to get P plus I beta minus beta, no P there at the end. And we divided by 1P on the right side, which we were allowed to do. And this is very, very similar to this. So this, again, is true if and only if I is equal to, is equal to 1. And we can, again, choose the I parameter to be 2 also. Cool. So what you should see from this is that you can actually show that multiple languages that are very similar are all non-regular just by generalizing them, do the proof in the generalized case, and then specialize it based on the languages at the very end, instead of having to do all the work over and over and over. So here, L1 and L2 are not regular. I'm not going to claim that L3 is not regular because it very well could be that f of m and n could just be 0. So if we define this function to be 0, then this is L3 is exactly the same as 0 star 1 star because the zeros and ones have nothing to do with each other here. The only tying together that we have is in the 0 bit in the original two languages. Whereas if we get rid of that right here, then we can't claim anything. And even if this was just M, you can actually show that this is, I'd have to think about it, but but you can't claim anything based off of this. F could be technically anything here. So L3 we can't claim as regular or not regular, it depends on F, but L1 and L2 are definitely not regular. Okay, so let's prove that this language is not regular. So here it's all strings of the form 0 to the n, 1 to the m, where n is not equal to m. So this is a very challenging language, but I'm going to show you a really nice trick that I've done on the channel already, but I'm going to do it again here. So let's again suppose that this thing is regular. So suppose L were regular, then what we know is that there exists a pumping constant P, exists a P for L. Okay, so then now what we need to do is we need to pick a string that is in the language and length at least P. So you may pick, okay, choose W equal to 0 to the P plus 1, 1 to the P. And that's actually pretty reasonable. It's a reasonably good choice because it's length at least P. The two exponents are not the same, so we're good to go then. It turns out that this won't work because if I put more zeros in to the left side, then I'm toast, right? Because I'm going to have more zeros and I'm trying to get out of the language, meaning that we have exactly the same number of zeros. The same number of zeros and ones. But if I put more in, then I'm going to still have more zeros and ones, and that's not good. If I try to pump down because I want to have these two be the same, then I could subtract 1 from here, but I got to look at all decompositions, and I might not be able to get exactly 1. I might overshoot the mark, and then now they're still not equal, and I haven't left the language. So we're going to use something that I've done on the channel, and you could search for it, but I'm going to show you it again here, called the p factorial trick. It's very tricky. And I did it in orange because of Halloween, obviously. But so this string will not help us. Instead, let's pick this string. 0 to the p, 1 to the p plus p factorial. Let me think. How did you come up with that? So I'll give my reasons at the end, but the basic idea is, remember when we tried to pump down here and we couldn't get nailed down exactly 1? Well, here, the number of things we take away could be anything from 1 up to p. So I don't know what that is, what number it actually is. It's some number between 1 and p. So let's just do something that if we added it over and over and over and over, regardless of whether it's 1, 2, 3, up to p, whatever it is, we will eventually hit the same target, which is p factorial. And why p factorial is because it's equal to 1 times 2 times 3 times blah, 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 up to p. So if I pick, if it happened to be 5, for example, then and let's say p was 10. So the number of characters I'm adding or deleting is 5, and p is 10. Well, 10 factorial divides p, or 5 divides 10 factorial. And so if I add 5 over and over and over, I'm eventually going to get there. An open question is whether or not you can do better than this, but this is totally fine for our purposes. So we got to look at all decompositions of w into x, y, and z according to the rules, where x, y has length at most p and y has at least 1 character. Well, we know that the first p characters are zeros, so we know that x and y are only zeros. So here we know that x is going to be some number of zeros, let's call it alpha. Y is going to be some number of zeros, call it beta. And we know that since y is non-empty, beta is at least 1. And z is the whole rest of the string. So we got p minus alpha minus beta, 1 to the p plus p factorial. Still there. Okay, so then now we want to see when is this thing in the language, and we want to pick an I for which it's not in the language, because we want to contradict what the pumping lemma says. So we want to choose an I such that x, y to the I, z is not in L. Okay, but we better figure out when it is in the language so that we can figure it out later. Okay, so what is x, y to the I, z? Well, let's just copy down the pieces. So we have 0 to the alpha, 0 to the I beta, 0 to the p minus alpha minus beta, 1 to the p plus p factorial. And let's collapse the zeros again. So we have 0 to the p minus, so the alphas get killed off, I should say. P plus I beta minus beta, 1 to the p plus p factorial. So what we can show here that this thing is in the language if and only if these two numbers are different. It's in the language if and only if they are different, because that's what the language is defined to be. So p plus I beta minus beta is not equal to p plus p factorial. So if and only if, well, we can subtract the p on both sides as equivalent. So I beta minus beta is not equal to p factorial. So let's factor the left side. So beta I minus 1 is not equal to p factorial. Well, since we gotta make an assumption. So since 1 is less than beta, so beta is at least 1, that's the condition, but it's also at most p. Because the first two pieces are of length at most p, well, the second piece, therefore, is at most length p. So that implies that beta divides p factorial. So if you haven't seen this notation before, this means that b is a divisor of this. So we can divide by beta on both sides, and I have an integer on both sides. So if and only if I is not equal to p factorial over beta plus 1. So as long as I is not equal to this specific number, then we're in the language. So let's pick that number to get out of the language. So let's choose I to be p factorial over beta plus 1. And that's it. And if you substitute it back in, then we're going to have the same number of zeros and ones. So a very complicated route to a problem that's very, very similar to a different one, which is way easier, which shows that getting two numbers to be equal is way harder than getting two numbers to not be equal, because there are a lot more numbers that are not equal to something than there are equal. Cool. So we have shown that 0 to the n, 1 to the m, where the two exponents are different, is not regular. All right, so let's prove that this language, 0 to the n, 1 to the m, where n is less than, strictly less than 3m, is not regular. So this turns out to be a very standard proof. So let's suppose that L were regular. Then by the pumping lemma, there exists a pumping constant P. I'm just going to abbreviate it to exists a P for this particular language L. So now what we need to do is we need to pick a string that is in that language L and has length at least P. So let's think, well, let's pick a string that has some number of zeros, some number of ones, and the number of zeros is strictly less than 3 times the number of ones. So what we want is a lot of zeros, because multiplying the number of ones by 3, that's in the range of where n needs to be, because we want to eventually contradict this. So let's choose, let's see, so what can we pick? Well, what I'm going to do is I'm going to pick p1s to start with. And what we need is that the number of zeros is less than 3p, because that's what the condition up here is saying. So what I'm going to do is I'm going to pick 0 to the 3p minus 1. So this is just barely in the language. If I had one more 0, then it's going to immediately leave the language. And in fact, that's exactly what we're going to try to do. So this is the string that we're going to pick. It's in the language because it matches the condition, and it has length at least p. In fact, it has 4p minus 1, which is definitely at least p. Cool. So what we need to do now is we need to look at all decompositions of this string into those 3 parts, according to the rules. So look at all decompositions, I'm going to abbreviate it to decomps again, of w into x, y, and z. And the rules are that x and y have length at most p, and y is non-empty, so y has length at least 1. So what are these? Well, x, y has length at most p, and the first p characters at least are zeros, so we know that x and y parts are consisting of zeros. So x is some number of zeros. I'm just going to call the number of zeros alpha. Y, I'm going to call the number of zeros beta, because they may be totally different from each other. Beta is at least 1, because we know y is non-empty. And z is the whole rest of the string. Well, we have 3p minus 1 zeros in total, minus alpha minus beta from the x and y taking that many zeros. And then we have all of the ones still in there. Okay, so this is just one, all possible decompositions are of this form that we ever need to consider. So what we need to do now is to choose some value I, some number I, such that x, y to the I, z is not in L, because we want to contradict the for all statement in the pumping lemma. So let's look at what x, y to the I is. So x, y to the I, z is, let's just copy the pieces down. So we have 0 to the alpha, 0 to the I beta, because we have I copies of y, and then I'm just going to copy z down. Oops. So I'm going to do it again. So 0 to the 3p minus 1 minus alpha minus beta, 1 to the p. So this run of zeros, we have a run of zeros here, so I can just collapse the exponents down. So the alphas are going to get killed off, plus alpha minus alpha. So here we're going to have 0 to the 3p minus 1 plus I beta minus beta, and then all of the ones are still there. So what we can reasonably conclude now is that this thing is in L if and only if the number of zeros is strictly less than 3 times the number of ones, because that's exactly what the language is saying. So it's in L if and only if 3p minus 1 plus I beta minus beta is strictly less than 3p, 3 times the number of ones, which is what that is. So this is if and only if we can minus the 3p on both sides. It's exactly the same, it's equivalent expression. So minus 1 plus I beta minus beta is less than 1. And then I'm just going to algebraically manipulate things. Oops, this needs to be 0, because I subtracted 3p on both sides. So then I add 1 to both sides. So I beta minus beta is less than 1. And then let's see. So if we pick an I such that this left-hand side is either 1 or bigger, then we're done. I claim that we can pick 2 for this. So let's choose I equal to 2. Well, then what happens is 2 beta minus beta is equal to beta. And we know that that is at least 1 because the part that we pump is non-empty. So this thing is at least 1. And so that contradicts the fact of this being less than 1. And so it is not in the language for that reason. So xy to the power 2, z is not in the language. And then therefore that contradicts the for all statement saying that based on the assumption that this were regular. And so therefore it is not regular. Okay, so let's prove that this language is not regular. So n squared up here is for all integers at least n, at least 0. So this represents a perfect square number of zeros, okay? So like 0 zeros are in there, so the empty string, or 1 0, or 4 zeros, or 9 zeros, 16 zeros, etc. And we claim that this is not regular. So let's proceed as we would normally do. Suppose L were regular. Then what we know is that there exists a pumping constant P for this language L. Then what can we do? Well, we need to pick a string that's in the language. So the usual technique is to substitute the P into the exponent right here where n is, not n squared, it'd be n. So the string that I'm going to pick here, choose w equal 0 to the p squared. Well, that's clearly in the language because I just substituted the number in. And p squared is always at least p when p is an integer. And so that's all that we actually need. It turns out that this string does work. Generally, if you have a string that's in the language and long enough, it's not necessarily going to work, but in this case it does. So what are we going to do? Well, we got to look at all decompositions of this string into those 3 parts. So look at all decomps of w into x, y, and z according to the 3 parts. Well, since the whole string is zeros here, we know that the x part is going to be some number of zeros, y is some number of zeros, and z is some number of zeros, because the whole string is zeros. Let's call the x part alpha, number of zeros, y is beta, number of zeros, where we know beta is at least 1 because y has to be non-empty. And then the z part is p squared minus alpha minus beta. Okay, so let's think. Well, here what I'm going to do is I'm going to pick a particular choice of I. So actually, first off, what do we need to do? Well, we need to choose some value I such that x, y to the I, z is not in the language, because that would contradict the for all statement of this being in the language. And then it will show us that it is not regular. Well, here, I'm going to pick a particular choice of I, and we'll see why it works. The reason for that is it's hard to get this to work in the general case, but if you look at a specific example, it's a lot easier. So what we're going to do here is I'm going to pick I equal to 2. Okay. It turns out I equal 3 also works, but I equals 2 is the one that is usually done, and the one I'm going to do here. So what is this string? X, y squared, z, and we want to show that it's not in the language. We don't know that it actually is not in the language yet, but we need to show it. So let's just copy down the pieces. So 0 to the alpha, 0 to the 2 beta, because I have 2 copies of y here. And then the z part, which is just copied straight down from the decomposition upstairs. And then when the dust settles, the alphas get killed off, and one of the betas gets killed off. So I'm going to have p squared plus beta here. Okay. And what we need to show or prove is that this thing is an L if and only if p squared plus beta is a perfect square. Well, let's see. So we know that p squared is strictly less than this number that we just derived. And how do I know this? And I'll actually put it below. So we know that because the beta itself is at least 1. And we know that because the part that we pump, which length is beta, has to be, the part that we pump is non-empty. So the number of characters must be at least 1. So this thing is at least p squared plus 1, but it could be a lot higher, but it's definitely at least 1. So we know that it's not equal to this perfect square right here because it's strictly larger than it. But it turns out that this thing is always at most p squared plus p. And how do I know that? Well, I know, let's put it below. I know that because the length of xy whole thing is at most p, which implies that the length of y is at most p, and the length of y is beta. So the largest that the length of y could ever be is p characters. So this thing is at most this. It could be a lot less, but it's certainly at most this. But I actually claim that this is strictly less than the next perfect square upward after p squared. So this is a perfect square. This is clearly a perfect square. And I claim that there's a strict inequality there. And how do I know that? Well, let's see. So this right-hand side is equal to p squared plus 2p plus 1. And the reason it's a strict inequality is because of that. It's because of that little bit right there. So that plus 1 gets that this is a strict inequality. So what we've derived here is that the length of the string that we just made is not equal to that perfect square because of the strict inequality, and it's not equal to that perfect square because of that strict inequality. And there's no perfect squares in between these because they are consecutive perfect squares. And so therefore this length, whatever it is not ever a perfect square. And so that's how you show that this is not a regular language, because if it were, then we would always hit a perfect square no matter what I value you choose, but we just chose one where we landed on a non-perfect square, this thing right here. So this actually gives you good reason to why the I equal 3 one I mentioned earlier also works. Because if you substitute I equal 3, you're going to get a p squared plus 2 beta here. And then here, the upper bound will be p squared plus 2p, which is still going to be strictly less than p squared plus 2p plus 1. So the I equal 2 and the I equal 3 also work. I think maybe the I equal 0 one also works, but I haven't checked. But higher ones, it's a lot harder to make sure that it's not actually a perfect square, because it could potentially be equal to this one if it goes any higher than p squared plus 2p. Okay, cool. So that's how you show that the perfect squares language is not regular. So I want to prove that this language, which is the set of all strings of zeros that are a perfect power of 2, for any power of 2 that you want, is not a regular language. So, for example, in here, we have a single 0, which corresponds to when n is 0. 2 to the power 0 is 1, so that's 1 0. We also will have 2 zeros, and then 4 zeros, and then 8 zeros, and etc. So I want to convince you that this is not a regular language. So let's suppose that it were regular. So suppose L were regular. Then what does that mean? That means that there is some pumping constant P for L. So there exists a P for this language L, and I'm just abbreviating that to say exists a P. So then now what we need to do is we need to pick a string that is in that language and of length at least P. So let's choose some string W. Well, the usual convention is to place the P wherever there's the variable in the exponent. So here I'm going to put 2 to the power P. Well, 2 to the P is definitely at least P, so that's no problem. And this is in the language because I just substituted the variable in, so that's no problem. So what we need to do then is to look at all decompositions. Look at all decompositions of this string W into X, Y, and Z according to the rules. So here, since the string is all zeros, we know that X is some zeros, let's call it alpha, the number of them. Y is some number of zeros, let's call it beta. And Z is the rest. I'm just going to be lazy and say rest here. So then now what we need to do is we need to choose a value I, so some number I, such that X, Y to the I, Z is not in L, because it would contradict the for all statement that that no matter what I you pick, you always stay in the language, but here we want to find one where you get out. So let's think. Well, so here we're dealing with perfect squares. So so let's actually look at this. Let's look at this in general. So what is X, Y to the I, Z? So that is equal to, just copy down the X piece. Then I have I copies of the Y piece, so I times beta, number of zeros. And then the Z part, well, that's going to be 2 to the power P minus alpha minus beta, because we had 2 to the P to start with. The X piece took alpha away, and the single Y took a single beta away. And that's the whole string. So since we have a whole bunch of zeros, we can collapse them together to get a single exponent. Well, the alphas are going to cancel. So I'm going to have 2 to the power P plus I minus 1 times beta. So what we can infer from this is that this thing is in L if and only if that exponent is a perfect square. So 2p plus I minus 1 times beta, not a perfect square, is a power of 2, I should say. Power of 2. Okay. So let's see. So what we can do is to think, well, if we set I equal to 1, then this thing would be 0. And so 2 to the p plus 0 is 2 to the p, which is a power of 2. So what if we set I equal to 2 as an example? So let's choose I equal to 2. Well, that is 2 to the p plus a single beta. Well, we know that beta is at least 1. So this is strictly larger than 2 to the p because beta is at least 1. And it's at most 2 to the power p plus a single p because the beta is at most p. And how do we know that? Because the x, y pieces together are of length at most p in total. And what we're asking is, what is the length of y by itself? And that is at most p. So that's what we get here. So let me actually write where all this comes from. So that inequality comes from the fact that beta is at least 1. That one comes from the fact that beta is at most p. And I'm going to do one more inequality, which is that this is at most 2 to the p plus 2 to the p. And we know that is true because p is always less than 2 to the p. Okay? And what we know over here is that this is 2 to the p plus 1 because that's just what the definition of perfect squares, powers of 2 are. So here, what we can actually infer is that 2 to the p plus beta could be equal to this one, except what we're going to do is we know that it's not just single less than or equal to, it is a strict inequality. It's strictly less than 2 to the p. And if it wasn't, we can just pick a higher value of p if it wasn't large enough, but it always is, so there's no issue here. So it's not equal to this power of 2, it's not equal to that power of 2, and these two are consecutive powers of 2. So it's kind of like the perfect squares proof, except now we have a slightly different thing that we need to check right here, which is that p is strictly less than 2 to the p. And so since it's strictly between two consecutive powers of 2, it can't be equal to either one of them. And so it itself is not a power of 2, implying that this language of perfect powers of 2 is not a regular language. Okay, so I want to prove that the language of all strings of zeros, which are of prime length, is not a regular language. So this is actually one of the more complicated pumping lemma in the sense of traditional pumping lemma proofs, but we're going to get through it. So we always start off every pumping lemma proof by supposing that L were regular. Then we know that there exists a pumping constant P for L, so that implies there exists a P for L. I'm just shorthanding it here. And what we need to do is we need to pick a string that's in the language and long enough, meaning that it has length at least P. So let's choose W equal to 0 to the P. It's clearly of length at least P, and the P's match up, so therefore it's in the language. Except it might not. So this P can be any integer. We don't know necessarily whether it's prime or anything. So we don't know whether this thing is of prime length, which is kind of crummy. So the way to get around this is use the fact that there are infinitely many primes. So whatever this number is, there's always a prime larger than it. In fact, there are infinitely many primes larger than it, although that's not as important. So what I'm going to do here is I'm not going to do this. I'm going to do this. And here's how I'm going to write it. So I'm going to pick the next prime above P. So I'm going to pick 0 to the R, where R is the next prime after P. Okay, I'm actually not going to do that either. and we'll see why. So I'm going to actually do after p plus 2. Okay? Well, there's always a prime at least p plus 2, so that doesn't change anything. And since it's more than p, therefore this is of length at least p, and it's in the language because we forced it to be a prime, and so therefore that's not an issue. So you may think, okay, why is there a plus 2 here? So it goes back to the definition of what a prime is. So a prime, remember, is a number where the only way to divide it into it is either itself or 1. There's no things that are at least 2 that multiply into p. Okay, so where does this plus 2 come from? It comes from, we need to be able to exhibit 2 things that multiply to the length of the string's length. And the way to do that is to try to break up the string in a nice way so that we have 2 things that are of both length at least 2, and so therefore the length of the string is not prime. Why do we want a string that's not a prime? Because we want to get a string that's not in this language, because we start off with a string that's in the language, and we want to end up with a string that is not in this language. Okay, so we need to look at all decompositions, look at all decomps of this string w into x, y, and z according to the rules. Well, the whole string is 0, so it doesn't matter. And I'm not going to actually exhibit the 3 pieces because it's just not going to matter. Let's see. So eventually what we need to do is we need to choose a value I such that x, y to the I, z is not in the language. Okay. Well, we don't know what this is. So we don't know what this length is, but we eventually need to exhibit an I for which it leaves the language. So since the string is only zeros, so the only thing that really matters here is the length of the string, not the string itself, because it's just all zeros. So let's try to look at that length. Oops. So I want to look at the length of, not w, I want to look at the length of x, y to the I, z, whatever it is. Well, this is equal to the length of xz, xz, plus I times the length of y. So why is this true? Because I have a single copy of x on the right side, a single copy of z over here, and y to the I, that's just I copies of y. So that's just I times the length of a single instance of y. So it is literally the same string because it's all zeros, but I'm only considering the length of the string. Okay, so what can we infer from this? Well, we know, based on the pumping lemma conditions, that this thing is at least 1. We know that the length of y is at least 1. Okay, how do we get from at least 1 to at least 2? Because we need 2 things that are both at least 2 to multiply into the number. Well, we add 1 to it. So what we want, what we want is the length of y plus 1 times something, and we want that thing to be also at least 2. We know that thing to be at least 2 because we forced it to be. But we need something in here that is also a length at least 2. And that's where the plus 2 from before comes into play. Because it turns out that we can sub into here the length of xz, which comes from this. And why can we do that? Well, let's see. We know that the pumping lemma condition says that the length of xy is at most p. So the length of w then, which we constructed earlier, is at least p plus 2, because we did that little plus 2 thing, and p might itself be a prime in the absolute worst case, but even in that worst case, is at least 2 more. So that implies that the length of z itself is at least 2. we know that to be true because even if xy took all p characters at the beginning, there's still 2 more left, and z is the only thing left in the string to take any characters. And so the length of z itself is at least 2, and x may be empty, maybe not, but it doesn't matter. It's at least 2. So, but how can we get from this line to this line? It's by subbing that value of I. So the value of I that we're going to pick is the length of xz. And if you actually check, that actually works out. Because if we actually compute this, so this is xz's length plus the length of xz times the length of y. And since we got an xz in both cases, I'm just going to factor it out. And we're going to get exactly the same expression that we had before. Okay, so this is an interesting example of the pumping lemma in that the value of I that you pick depends on the decomposition, but that's okay. As long as you find some value of I for which you get out of the language, and we did, that's all that's needed. So we found a value of I, we constructed something that is some number that's at least 2 times another number also at least 2. So whatever that number is, which is the length of that string, has to be composite. It's not prime. And so therefore, this string is not in the language. And because of that, that shows that the language is not regular. Because if it were, it would always be a prime. But we found an example of where it is not a prime. So that's how you show that the language of primes is not regular. All right, so we have to prove that this language, which is all the strings of the form 0 to the m, 1 to the n, where m over n is an integer. So here this is just saying that the number of zeros is a multiple of the number of ones. So as an example, if we have, let's say, 6 zeros, then I can have 3 ones because 6 over 3 is 2, so that's an integer. But if I struck one of those zeros out, then this thing would not, that string would not be in L because 5 over 3 is not an integer. And I want to show that this thing is not regular. So let's suppose that it is. So suppose that L were regular. Then that means that there's a pumping constant P for L. So let's go ahead with that. So there exists a P for L. I'm shorthanding this. Okay, so then now we got to pick a string that's in the language and of length at least P. So, and we also have to, of course, we need to have the number of zeros divided by the number of ones being an integer. In other words, the number of zeros is a multiple of the number of ones. So let's go ahead and choose a string, and this string will not be useful for us, but I just want to show it anyway to give you the idea. So here, let's look at this string. So we definitely have at least P characters because there are 3 P characters here. And this thing is in L because 2P divided by P is 2, and that's an integer. So why would this string not be a good choice? So let's think about what happens. What we want to do is we want to pump this string so that we get into, we get a string that is not in L. So in other words, the number of zeros is not a multiple of the number of ones. But in order to do that, we have to pump in the zero part because that's one of the conditions of the pumping lemma. So if I increase the number of zeros, then it might be that we increase it by P zeros every single time. And that is a valid decomposition of the string according to the rules. So it could be that we can have any number times P over here and P over here, and we'll never escape the language there because M over N is not an integer. It is always an integer there because we have 1 P over here and some integer times P over here. If you pump downward, you may think, okay, that's fine because we're going down here and it's not twice as much. It could be that we take away P characters here. And so we'll have 0 to the P 1 to the p, and that will not help us very much. So there are actually 2 routes we can go. So one route is we can just pick 0 to the p, 1 to the p, and then pump down. But the problem is that if we tried to do, let's just say we tried to do that, then what would happen is, what if we had the decomposition where we took away p characters? So the x and y bit, the first 2 parts, it occupied all of these zeros right here. Then what would happen is that if we took away all p of those characters, which we're allowed to do when pumping down, it might be that we have 0 zeros there, and so this fraction will be 0, and that's not really allowed. That is allowed according to the language, but it's not the conclusion we wanted. We wanted to have something that is not an integer, so this idea will not help us. However, what if we did this? What if we said, okay, let's pick some other fraction. We gotta pick a fraction for which it is an integer when dividing here at the start, but we will end up in something that is not an integer. So let's say 3p here and 2p here. Oh, sorry, 4p. 4p, that's what I wanted. So then let's see. Let's look at all decompositions now. So look at all decompositions of w into x, y, and z. Well, since x and y are at most p characters, and the first p characters are all zeros, we know that the x and the y bit are some number of zeros only. Let's call them alpha and beta as the number of zeros. And z is the rest, which I'm not going to bother writing down. So then we need to choose an I such that x, y to the I, z is not in L. Okay. Well, it's pretty clear. Well, actually, no, it's not so clear. So we got to pick an I for which is not in the language. So let's actually look at this string x, y to the I, z. So that's 0 to the alpha, 0 to the I beta, and I'm going to put down what z actually would have been. So it would be 4p, because that's what we started with, minus alpha minus I beta. Yeah, that's right. It's not I beta. Sorry. It's 4p minus alpha minus beta, because that's what the y part had. I really should have done that. And then we have a 1 to the 2p there. So then let's shrink down all of the zeros here. So the alphas get killed off. So I'm going to have 4p plus I minus 1 times beta, because that's how many betas I have, and then 1 to the 2p. So it's very obvious that this thing is in the language if and only if the number of zeros is a multiple of the number of ones. So 4p plus I minus 1 times beta over 2p is an integer. Okay, that's the only way it could possibly be in there. So let's actually substitute a value in. So let's put in, let's say I equal to 2. We can't put 1 because that's what the original string was, and that's in the language, so we can't prove it's not in the language if we choose I equal 1. So let's look at I equal to 2. So that's 4p plus beta over 2p. But if we look at this, we know from the pumping lemma statement that beta itself is between 1 and p. So where this comes from the actual statement, one of the things that we need, that the part that we pump is non-empty, and this part says that the first 2 pieces have length at most p in total, and so that's where this comes from. So here, the only way that this could really be an integer is if beta is equal to 2p, because it can't be 0 according to this, and so the next higher point would be 2p for beta, because then this would reduce to 3. If beta was 0, this is 2, and there's no number in between 2 and 3. So therefore, if we pick I equal to 2, no matter what beta is, this thing is not an integer, and so therefore we are not in the language as a result of that. If you pump down, so if we like chose I equal to 0, that also would work. We would have 4p minus beta, and the only way that that could be an integer is if we had 2p upstairs, which means that beta would also have to be 2p, and that's just impossible according to this. So that is a quick proof to show that this language is not regular. The key to understanding this is that you have to be able to think about whether or not the string makes sense. So the 2p 1 to the p example seemed reasonable until you thought about, okay, all the decompositions, got to handle all of them, including the ones where the length of y is equal to p, and that's where the problem arose in that case. Here, the gaps between where the left side divided by the right one is an integer are much wider, and so that's why this allows us to escape the language, whereas before they were short enough to allow us to stay within the language. So this language is not regular. All right, so let's prove that this language is not regular, which is the set of all strings over 0, 1 star, such that the number of 0, 0s and 1, 1s in W is the same. So as an example, if we look at the string 0, 0, 0, 1, 1, 1, and maybe a 0 at the end. So let's count the 0, 0 occurrences. So there's 1 right there, there's 1 right there. They can be overlapping possibly. There's a 1, 1 there, and a 1, 1 there. And so since there are 2 occurrences of each, therefore this string is in the language. And if we took off that 0 on the end, that doesn't change anything. However, if we took off this 1 right here, then it's not in the language anymore. If we deleted the first 0, then it's back in the language, okay? So let's prove that this thing is not regular. So, as always, we need to suppose that L were regular. Then that means that there exists a pumping constant P for L. I'm just going to abbreviate it as exists a P. So we need to find a string that is in the language and has length at least P. So it has to have the same number of 0, 0 occurrences as 1, 1 occurrences. And there's a lot of different strings that you can actually pick in this particular case. I'm just going to do a common one that is kind of similar to the example that we did a little earlier. So I'm going to choose W to be equal to 0 to the P, 1 to the P. And you think, huh? There's no 0, 0s in there, Ryan. There's no 1, 1s in there. Au contraire. So let's think about what this string actually is. It's a whole bunch of 0s and then a whole bunch of 1s. So let's think about where the 0, 0 occurrences are. It's right there, right there, right there. And it's kind of like this staircase pattern that goes down, and then the 1, 1s occur in the same way. In fact, there are P minus 1 occurrences of 0, 0 in there. Try to think about why that is. And P minus 1 occurrences of 1, 1 in there for the same reason. All right, so then now we need to look at all decompositions. Look at all decompositions of W into X, Y, and Z according to the 3 rules, such that X, Y has length at most P and Y has at least 1 character in it. So since X and Y are the beginning of the string and have at most P characters, they must live entirely within the 0s. So I'm going to have X be some number of 0s, let's say alpha of them. Y is 0 to the beta, some number of 0s. And let's say Z is 0 to the P minus alpha minus beta, because that's the number of 0s left. and then 1 to the p at the end. So now we need to choose an I for which the number of 0s and 1s is different. And so more precisely, we need to choose an I such that x, y to the I, z is not in L. So it's not in L. Okay? Well, what is this? If you actually compute it, it's going to be this string. It's going to be 0 to the p plus I minus 1 times beta, and then 1 to the p. So here, because we have the alphas get killed off, we have I beta right here, because that's how many choices of y we have. And then we have a minus 1 beta from this. So that's where the I minus 1 comes from. So this thing is in L if and only if the number of 0s is equal to the number of 1s. And we want to show that the numbers are actually different, or choose an I for which they are different. So what does that mean? So that means, well, what is the number of 0 occurrences here? So the number of 0s is going to be, since this is a contiguous range, it's going to be 1 less than that number. So it's going to be p plus I minus 1 times beta minus 1. That's the number of 0 occurrences. And then the number of 1 occurrences is going to be 1 less than the other range's length, which is going to be p minus 1. So this thing is in L if and only if these two numbers are the same. So I'll go back to red. So this is if and only if p plus I minus 1 times beta minus 1 is equal to p minus 1. Well, we see a p minus 1 on both sides, so let's kill those off. So this is if and only if I minus 1 times beta is equal to 0. And that would imply that either I is equal to 1 or beta is equal to 0. Beta is not 0 by definition, so that's not 0. So let's choose some value of I that's not 1. Let's pick 2. You can pick, by this, you can pick any value of I that you want as long as it's not 1. Okay, so that shows us that we have arrived at a string that is not in the language, and that would contradict the for all statement in the pumping lemma there. So therefore, we have shown that this language is not regular. Try to generalize this. So if you substituted this with 0, 1 and 1, 0, it turns out that that is regular. And if you have done, there's a whole bunch of strings, pairs of strings where it is regular, and a whole bunch of pairs of strings where it's not regular. And it turns out work that I've done and some other people have done have actually shown when is this regular and when is it not. And try to actually think about, is there some kind of general pattern that you can see? And there is, and it's really cool. So we have shown that this language is not regular. Okay, so let's prove that these two languages are both not regular. So they're very, very similar. So we have W ranging over all possible binary strings here, 0s and 1s. And the first language has that we have exactly the same W on both sides of some pound sign. And in the second case, we have the exact same string twice. So effectively, L1 is exactly the same as L2, except you stick a pound sign in the middle. And I want to show that both of these are not regular. So let's go about doing this. And what I'm going to do is I'm going to prove that L1 is not regular. And actually, no, I'm going to prove that L2 is not regular. And then immediately, or we'll see how to get that L1 is not regular. So let's suppose then that L2 is not regular. Then that means that there exists a pumping constant P for L2. And we need to pick a string that's in the language and at least P in length. So let's go ahead and do that. Let's choose some string, and this string will not work, and I'll explain why. So let's pick 0 to the p, 0 to the p. It's in the language because it's the exact same string twice. It's length at least p because it's length 2p, so that's good enough. But this string won't help us. Why? Well, we need to eventually try to pump our way out of L2. So we want to have two pieces that are completely different from each other. The problem with that is, since this string is all zeros, if the decomposition has the pumped piece have 2 or even an even number of characters, then if I pump up or down, then I'm going to have always have an even number of zeros. And since if I have an even number of zeros and the whole string is zeros, then the two halves are exactly the same. And that doesn't help us. So yeah, so let's not do this. Instead, let's have some ones mixed in. So if I have 0 to the p 1, 0 to the p 1, then effectively these two sets of zeros are separated from each other, and then that causes some problems with trying to keep the same number on both halves. So let's try to work with this. So we need to look at all decompositions of w. So I actually should note here, this w is not the same as that w. This is just a variable over a set. This is a particular string that I'm choosing. It's not being pasted up here. It's just they just happen to have the same name. This w is completely different. You should use a different variable name here. I'm not so good at that. But I'm using the w here because it's consistent with every other proof I've done. Okay, so look at all decompositions of this specific string where the two halves are identical to each other. And we want to break them up into those three parts, x, y, and z, according to the rules. Well, here, x, y has length at most p. That's one of the rules. And since that's the start of the string, they must only contain zeros because the start of the string has p zeros in it. So we know that x has some number of zeros, let's call it alpha. Y has some number of zeros, call it beta, and beta is at least 1. And z is the rest of that run of zeros. So p minus alpha minus beta, the single one there. Then 0 to the p, we never touch that region. And then the final one at the end. So what we want to do is we want to choose some value I such that x, y to the I, z is not in L2. It's not in L2, okay? So let's look at it. What is the string x, y to the I, z? We'll just paste all the things down. So 0 to the alpha, 0 to the I beta, 0 to the p minus alpha minus beta. It's just copying everything down, except for the y to the I piece because we have I copies of it. We have a run of zeros, so let's compress them. So we'll have p plus I minus 1 times beta, a single one, and then 0 to the p1. So this thing is, I'll go up here. So this thing is in L2 if and only if the two halves are the same. So it's a fallacy to think that the middle is right here anymore. It's not. So the middle has actually moved, depending on the choice of I here. So if I is 2 or more, then this line has moved left because we put more stuff over here. So the middle point is over in here somewhere, in the 0 somewhere. Whereas if I is 0, we can't choose I equal to 1 because that's the original string. If we chose 0, then it moved over here. So let's choose some I at least 2. If you choose I equals 0, you'll get a different conclusion, but it's the same. You'll still show that it's not regular. It's just a different conclusion. So that means if and only if the two halves are the same. The two halves are equal. Well, let's try to visualize what it looks like. So we have a whole bunch of zeros at the beginning, the single one, some smaller number of zeros there, and then the 1. But here, the midpoint is right in here somewhere. So that is the midpoint. But notice what happened here. So this right half starts with the 0, or it's actually not necessarily start with a 0, but it ends in a 1 for sure. The second half ends in a 1, and the first half ends in a 0. And so the two halves cannot possibly be the same because they in this case end differently. If you choose I equals 0, you'll find out that the two halves don't start the same. Okay, so you'll actually have a different structural problem depending on what actually happens. But here we know that the strings end differently, the two halves. This ends in a 0, this ends in a 1. So therefore the original string, this string that we just made, is not in the language L2, and then therefore L2 is not regular, because we contradicted the for all statement in the pumping lemma. Okay, so let's prove that L1 is not regular. So for L1, what would we need to do? I'll call the string W1. Well, we're going to do something very similar. We're going to have 0 to the P1, 0 to the P1. There are actually many other strings you're going to pick, not just this one. Well, let's think about what happens. So if we substituted the pound sign right there, and then let's see what happens. The pound sign is right there. The pound sign is right there probably. So then here, what are the things that can happen? Well, so let's see where the midpoint is. So the midpoint was right on the pound sign initially, but then because we put more stuff over here, it's on one side of the pound sign. So for a string to be in L1, it needs to be right on the pound sign, the midpoint, whereas here it moved past the midpoint. So it's a little bit more illustrative of where the midpoint actually is. But the languages are very, very similar in that you can prove that both are not regular just using one proof and adapting it for the other language. So here we have shown that these two languages are not regular. Okay, so let's prove that this language is not regular. So it's a little bit complicated to explain, but the basic idea is that we have a whole bunch of different strings delimitered, separated. So here we have a bunch of W's right here. So these W's, let's just say for convenience that they are strings in 0, 1 star, just purely for convenience. But here, every single one of these strings is different. So there's no duplicates among these end strings. Okay, that's all it is. Okay, there's no bound necessarily on how many strings we got, but we can have as many as we want as long as they're all different. Okay, this is just a formal way of saying that if you have different indices, then the strings corresponding them are different. If I look at W1 and W1, then clearly it's equal to itself. So that's not really useful. So let's prove that this thing is not regular. So let's suppose L were regular. Then that means that there exists a pumping constant P for L. I'm just shorthanding it here. So now the hard part is to pick a string. So let's think about what we would do. So we would choose W equal to something. And what you would think to do is to, let's say I'm going to pick 0 to the P and then pound sign some other stuff. Well, think about what happens. So if I have this at the beginning, then I'm going to be only pumping in this region right here, okay? Because that's one of the conditions of the pumping lemma. So let's just say we pump up one time, okay? If we pump up one time, then the number of zeros in this region is between P plus 1 and 2P. You must have at least one more 1 and at most P more zeros. Sorry, at least one more 0 and at most P more zeros. So what we can do then to try to get a contradiction, to get a string that's not in L from a string that was in L, is to say, okay, well, this thing can land somewhere between p plus 1 and 2p. Let's embed it in the string. So by embed, here's what I mean. So I'm going to have p plus 1 zeros here, delimitered, p plus 2 zeros, delimitered, and keep going up by 1 until I reach 2p. So note that this is way more than p characters. It's like p squared probably, or something like that. But notably that this is in the language, because each one of these runs is different than every other run. In fact, we didn't even need to have the one character here. But if we pump this region up one time, then we're going to have this region's length to be the same as one of these other ones. I have no idea which one, but we know that it must be in one of those somewhere. Okay, so then let's try to make this a little more formal. So we need to look at all decompositions of W into X, Y, Z according to the rules. So the rules say that X and Y have at most P characters. So in this case, since the string starts with P zeros, then we must have all zeros in the X part. Let's say alpha of them. And Y has beta zeros. Let's just say it can have any number of zeros as long as it obeys the rules and has at least one. And Z is the rest. Well, Z is going to be P minus alpha minus beta. That's the number of zeros at the beginning that are left. And I have all of these other ranges still there. Okay, I still got all those other ranges over there. And you could have done something similar if you wanted to pump down or pump up twice. There are many other things you could have done here. This is just the simplest example I can think of. So we need to choose I equal to 2. We're choosing I equal to 2 because that's what we started, what we wanted to do in the first place. And we want to show that this thing is not in the language. So we want to show that X, Y to that number 2 is not in the language. It's not in the language. So let's compute what that is. So X, Y squared Z. Well, we're going to basically just get a gain of beta in the first run. So we're going to get P plus beta, pound sign P plus 1, pound sign, etc., pound sign 2p. So this is in L if and only if Wi is not equal to Wj for all I not equal to j. Okay. Well, among the ones over here, they're unmodified. So therefore, any pair among here is they're automatically different, so we don't need to worry about those. The only thing is this one could be equal to one of these other ones. So this is true. This is in L if and only if P plus beta is not equal to P plus I for any let's see, between I is between 1 and P. Okay, I'm just encoding how many more I add to the initial P that I have. So I started with 1, which is right here, and I ended up with P, which is this one here. So this is if and only if beta is not equal to I for any I between 1 and P, but beta has to be one of those numbers because it's at most P and at least 1, which is a contradiction. So therefore, this is a contradiction, so therefore this string is not in the language, and so therefore this language of all these different strings that are different is not regular, because we can show that we can arrive at a string that is not in the language from a string that initially was in the language. Okay, so let's prove that this language is not regular. So it's the set of all strings that are not palindromes. Okay, so as an example, A, B, B, A, that is a palindrome, so it's not in L. But if I take away one of those characters, let's say that one, then it is in the language L here. So whenever you have a question to show something that's not regular, where it says is not something, a good technique is something called the P factorial trick. You can search it on YouTube if you wanted to. I made a video on it. Thank you very much. But I'm going to reintroduce it here. So let's try to prove that this thing is not regular. So let's suppose L were regular. Then there exists a pumping constant P for L. So there exists some constant P for this language L. So then now we got to pick a string that is in the language and length at least P. So let's choose W equal to, well, we got to pick something that's not a palindrome, and we want to arrive at something that is a palindrome, which is kind of hard because the things that you're going to be pumping can have a lot of different lengths. You want to make sure that you can always eventually arrive at a palindrome, which is kind of hard if you think about it. So what we're going to do here is this. Oh, actually, I should say ABB is not in there. I meant 0, 1, 1. That's in there. Okay, so let's pick, let's say 0 to the P, 1. I'd like to do 1, 0, and I gotta have some number other than P here, because if I put P here, then it's gonna be a palindrome. I want something in the language to start with. So what I'm gonna do is I'm gonna pick P plus P factorial. So this is something called the P factorial trick. The reason is that no matter what you pump over here, P factorial is a multiple of the length of whatever you pumped over here, and we'll make that more precise later. Okay, so let's look at all decompositions. So look at all decompositions of W into X, Y, and Z according to the rules. So X is going to be some number of zeros in this case. Y is going to be some number of zeros in this case, also because the first P characters are 0, and that's one of the rules. And Z is going to be the whole rest of the string. So P minus alpha minus beta, that's the amount left. The 2 1s in the middle, and then 0 to the P plus P factorial. I should check first. This is clearly a length at least P, and is not a palindrome because P plus P factorial is strictly more than P, so it's not in the language. So it is in the language, I should say. It is in L, it's not a palindrome, it is in the language. Okay, so now what we want to do is we want to choose an I, such that X, Y to the I, Z is not in L. In other words, X, Y to the I, Z is a palindrome. Okay, because that's what it means to not be in the language. Okay, so let's actually compute what this string is. So X, Y to the I, Z, that's going to be 0 to the P plus I minus 1 beta, the 2 1s in the middle, and then 0 to the P plus P factorial. The 1 1s in the middle are preventing the zeros from being squeezed together, and that means it already is a palindrome. So the 1 1s are kind of useful. You could have done with a single 1 instead of 2. I just happen to do 2 here. But okay, so this, what does it mean to be in the language? So it's in the language means it's not a palindrome if and only if the 2 runs of zeros are different, because the 1 1s aren't really contributing anything to whether this thing is a palindrome or not. So if and only if P plus I minus 1 times beta is not equal to P plus P factorial. Okay, so this is if and only if you subtract P from both sides, is I minus 1 times beta is not equal to P factorial. So that means if and only if I is not equal to P factorial over beta plus 1. And it's important to note that this quantity right here is an integer. And why is it an integer? Because beta is between 1 and P. So P factorial divides oh, sorry, beta divides p factorial no matter what it is because it's between 1 and p. And plus 1 obviously doesn't change whether it's an integer. So let's choose I equal to be that number. So let's choose I equal to p factorial over beta plus 1. And that allows us to have it be a palindrome now. So because this thing is an integer, that allows us to escape the language, the clutches of the language, and arrive at something that is a palindrome, but just barely, because you have this exactly one value of I that works. It just barely holds on, but eventually allows us to get in there. So that's pretty cool. So this was an application of the p factorial trick to show that this language of non-palindromes is not regular. All right, so let's prove that this language is not regular. So it's the set of all strings x and y. Let's say that x and y are in, let's say, 0, 1 star, where the two they have the same length and they are not equal to each other. So in other words, this is effectively saying even length strings where the two halves are not the same. Okay, that's all it means. So I've actually done this exact problem before on the channel. You can probably search it. And it's actually a pretty complicated proof. I'm just going to make a single segment on this. So let's suppose that this thing were regular. I want to show it's not regular. Then that means that there exists a pumping constant, exists a P for this language L. And what we want to do, of course, is to choose some string that is in the language. So that means that the two halves are not the same and has length at least P. So we're going to be using something called the p factorial trick. Why am I going to use such a thing? Because whenever you have something that is not equal to, and you want to arrive eventually at something that is equal to, because that's you need to show that this thing is not regular, you want to arrive at a string that is not in the language, meaning that either the length is odd, but we can't necessarily guarantee that the two halves are not, that the two halves are equal to each other. So I want to start off with a string where the two halves are not the same and arrive at the strings that are the same. So I'm using a p factorial trick because p factorial divides any number between 1 and p. Okay, so that's the reason why. And we'll get more precise on that. So it's going to be 0 to the p, 1. And let's say 0 to the p plus p factorial 1. Okay. And let's see. So the two halves are obviously not the same. So let's actually calculate the length of a string. So the length of w, just to make sure that it actually is even. Well, we have two ones here. So that's going to be 2 plus 2p plus p factorial, because we have two p's and a single p factorial there. So as long as p is at least 2, this number is even, and that's good. So so we might as well assume that p is at least 2, and if it happens to not be at least 2, so if p is smaller than 2, then we'll set p to be equal to the maximum of 2 and p. So as long as it is at least 2. And we're allowed to do that because as long as we pick a string that's long enough anyway, and we arrive at a contradiction, we're okay. So here, this string is definitely a length at least p. In fact, it's way more than that. But it's in the language because it's even, and the two halves are definitely not equal to each other. Because the middle is somewhere in this long run of zeros. And so the first half ends in a 0 and the second half ends in a 1. So they can't possibly be the same. All right. So let's try to look at all decompositions then. So look at all decomps of w into x, y, and z. And the decompositions look like this. So it's going to be alpha zeros for the x part, beta zeros, let's say, for the y part. Again, these are just any old numbers because if this is any possible decomposition, this is just saying what the length is. And z is going to be p minus alpha minus beta, 1, p plus p factorial, zeros, and then the 1. Okay, so then now we want to pick a value of I, so we want to choose an I such that x, y to the I, z is not in L, okay? Because we want to arrive at a string that is not in the language. So let's calculate what the string is. So x, y to the I, z, well, what is that thing? So if we just copy down all the pieces, it's going to be 0 to the alpha, that's just the x part, 0 to the I beta, 0 to the p minus alpha minus beta, and then 1, and then this whole mess. Okay, well here, we got a long run of zeros here, so let's collapse everything. Alphas go away, so I'm going to have p plus I minus 1 times beta, 1, p plus p factorial, 1. So the only way that this could not be in the language is if the straddle point was right there. So the midpoint was exactly there, which means that because of these singular ones right here, that means that these two runs are the same. So it's in L if they are different. Okay, so it's in L if and only if p plus I minus 1 times beta is not equal to p plus p factorial. The two runs of zeros are not the same in length. Well, I can subtract p from both sides, and that's the same conclusion. So I'm going to get a I minus 1 times beta is not equal to p factorial. And that turns out to be if and only if I is not equal to p factorial over beta plus 1. It's just rearranging things. And it turns out that this thing right here is an integer. And why is it an integer? Because beta is between 1 and p. And whatever that number is, it divides p factorial. Because p factorial is 1 times 2 times 3 all the way up to p. And adding 1 doesn't change whether the number's an integer or not. So, crucially, this number is an integer. So it's in L if I is not equal to this, but we want it to not be in the language. So let's choose I to be that number. So let's choose I to be equal to p factorial over beta plus 1. And so therefore, that resulting string is has both sides being equal. Okay, that's the only possibility of these two halves being exactly the same, because they have exactly the same halves. And so therefore, this string is composed of two things that are exactly the same, which is not what the language says. So note that we didn't care whether or not this thing was even in length. It didn't actually matter, because if it was odd in length, this thing is not in the language anyway, but we would have arrived there anyway. And this thing is definitely not odd in length anyway, so it doesn't actually matter here. Okay, the thing that mattered is that the two halves had the same length. Okay, and here they had to be exactly the same. So hopefully that was interesting to show that this language is not regular using the p factorial trick. Okay, let's prove that this language is not regular. So it's the set of all strings that are composed only of zeros, and they have a factorial number of zeros. So 0 factorial is 1, well, it's defined to be 1. So we would have exactly 1 0 in here. If n is 1, we would have 1 0 again. If n is 2, then this would be 2 zeros. If n is 3, this would be 6 zeros. If n is 4, that'd be 24 zeros, etc. So I want to show that this thing is not regular. So let's suppose that it were regular. suppose it were regular, then that means that there exists a pumping constant P for L, exists a P for this language L. Okay, so then now we want to pick a string that's in the language and has length at least P. Well, that's no problem. So let's choose W to be equal to 0 to the P factorial. So commonly the technique is to substitute the P for the exponent, the N, not the whole exponent, the N part. And clearly this is in the language because we defined it, the number P, and this is quantified over all N, so therefore P is in there. Well, P factorial is in here. And P factorial is at least P. So let's think. Well, those small values, 0 factorial is 1, the factorial wins. 1 factorial equals 1, the factorial is equal or larger, and that's fine. 2 factorial is equal to 2, the factorial is equal. 3 factorial is 6, so the factorial wins. And then factorial just keeps going up and up and up after that. So the factorial is always more than the original number. Okay, so what we need to do is to look at all decompositions of x, y, and z such that the length of x, y is at most p, and the length of y is at least 1. Well, here it's not really as important because the string is all zeros, so therefore we don't really care about what the actual decomposition is. We're just adding some or subtracting some number of zeros into the string. We don't care about the actual string. But let's write it down anyway. So x is going to be some number of zeros since the whole string is zeros. I'm just going to call this alpha. Y is going to be some number of zeros. Let's call it beta. So beta is at least 1, let's say. Well, actually, that's a rule. In fact, it's a rule over here. And then we have, well, what's the rest of the string? It's p factorial minus alpha minus beta. And so what we want to do is we want to choose an I such that x, y to the I, z is not in the language, okay? And the reason is that we want to arrive at a string that's not in the language from a string that we had, because that would contradict the for all statement in the pumping lemma. So let's compute what that is. So that's going to be x, y to the I, z, which is going to be 0 to the p, factorial plus I minus 1 times beta. And the reason for that is the alphas will cancel. I'm going to get an I beta out of this and subtract 1 beta out of this. So that's what we get here. So therefore, this string is in L. Oops, jumped the gun. So this thing is in L if and only if p factorial plus I minus 1 beta is a factorial of some number. Okay, well, let's see. So if let's just pick I equal to 2 just to see. It'll turn out to work, but let's see. Let's choose I equal to 2. Then that's effectively saying p factorial plus a single beta is a factorial. Well, we know that beta is at least 1, so it's not equal to that factorial right there. So let's write that down. So p factorial is strictly less than p factorial plus beta, because beta is at least 1. So let's write that guy down. So that's because beta is at least 1. It turns out to be, at most, p factorial plus p. And you may say, okay, where did that come from? Beta is at most p. Well, the condition of x, y's length being at most p, way up there on the right, that effectively says that the length of y is at most p, because x can't subtract anything out of the length. So that's at most that. Well, what is the next factorial? So that's going to be p plus 1 whole thing factorial, which is equal to p times, oops, my mistake, That's p factorial times p plus 1. That's just what it's defined to be. So if it's the case that this thing is strictly less than this, then we're done. Well, let's see. Well, we can actually kind of see this because adding p versus multiplying by p plus 1 is has this clearly going to be way bigger than just adding this. So it's adding a small number compared to the factorial times, compared to timesing it by something else, even bigger than it. So multiplying by a bigger guy versus adding itself, it means that this thing is way, way less than that. So these two are consecutive factorial numbers, whereas, and it's strictly in between them. So this length right here cannot possibly be a factorial because it's consecutive between two consecutive factorial numbers, and it's not equal to any one of them. So therefore, this factorial, this length, whatever it is not a factorial. And so therefore, this language is not regular, because if it were, we would always arrive at a factorial number, but we showed that if you choose the right value of I, in this case 2, you can show that you will not arrive at a factorial number. It's very similar to perfect powers of 2 and perfect squares, and try to see if you can generalize this to some arbitrary function up here. What has to be true about this function in order for it to be not regular? It turns out to be a very nice answer. So this language is not regular.